Hi there, and welcome to today's class. So, for today's class, we'll continue from our last class in our studies of fluid mechanics as a course. So, we dive into discussing fluid mechanics as a course. So, our last class, I'll drop the video to our last class on introduction to fluid mechanics, or perhaps if you want to, you can click on the link you see above you here, so to take you to our first class on fluid mechanics, where we discuss the definition of fluid mechanics, the branches of fluid mechanics, and also the properties of fluid. So we discuss the property of fluid from what we call from um, adhesion, cohesion, surface tension, capillarity, density, relative density, specific gravity, viscosity, and what have you. So last class there we stop about relative density. So our next task now, our next property we're going to be considering is called viscosity. So if you're familiar with our last class, you should know why I'm trying to discuss about viscosity now. So to understand the whole concept, try to check our video on our last class on fluid mechanics. So to understand all the whole concept, let's discuss viscosity as the 8 properties of fluid. Viscosity. Let's discuss viscosity. All right. By definition, viscosity is the opposition to the flow of fluid particle in motion. It can also be defined as the internal friction that occur between layers of a fluid particle in motion. That's the definition for viscosity. So let me explain the idea of viscosity. Um, you know, in a normal real life sense, if I take two objects, okay, let me say I'm using my hand. Let's say my hand are the two objects. If I rub these two objects together, if I keep on rubbing them together, at the long run, it will create an heat. There will be a friction, like an heat will be generated from these two objects rubbing each other, right? So the idea is that when two liquids are rubbing against each other, what would be generated from it? The thing that will be generated is called viscosity. So that's the idea behind the concept of viscosity. All right, having looked at the definition of viscosity, let's look at something important called Newton's law of viscosity. Newton's law of viscosity. All right, let's take the law that guides Newton's law of viscosity. Newton's law of viscosity says that the shear stress in a crude element layer is directly proportional to the shear strain or shear deformation or velocity gradient. So that's like the law to Newton's law of viscosity. So from the law I gave you now, I said the shear stress. So when it comes to science, we represent shear stress with a Greek symbol called tau. This is tau. This is tau. Shear stress. So I'm saying that the shear stress in a crude element layer is directly proportional to what? To the shear deformation or shear strain or velocity gradient. So if I'm representing velocity gradient, so velocity gradient becomes what? Du over dy. In science, if you hear the word gradient, so if I mean the word pressure gradient, it means what? Pressure over length. So for your level, the assumption is that when I'm discussing about gradient, it means that parameter over length. So if I'm saying pressure gradient, that becomes pressure over length. So velocity gradient becomes the velocity over length. So I'm saying the u over the y. The u represents initial velocity in what? In meter per second. True or false? True. This is the y. Y here represents height, right? Vertical distance and height. Height is measured in meters. So it's more of saying velocity over what? Over length. That's the concept. That's how I got to the u over the y. So as the mathematical expression for velocity gradient. All right, at this point here, let's get the SI unit for shear stress. We know that shear stress, of course, from the idea of stress. What's stress? Stress is the Greek stress is represented with the Greek symbol called sigma, which is what? Force over area. What's force? Newton. What's area? Meter squared. Let's get SI unit. The stress is measured in Newton per meter squared. So I'm hearing the word shear stress. So the idea is now I'm hearing the word stress inside shear. So I'm hearing this one comprises of two things: shear stress. So I'm still using the same SI unit. So the SI unit for shear stress is measured in what? In Newton per meter squared. Let's get the SI unit for viscosity. Oh, sorry, velocity gradient. I'm having the u over the y. What is the SI unit for the u over the y? SI unit. Let's get the SI unit for the u over the y. What we know is that I'm having the u over the y. We just said the u represents velocity, initial velocity in what? In meter per second, divided by the y in meters. Y is vertical distance, meters. So in mathematics, and this one here, mathematically, I'll be having meter over seconds. This division sign and meter. So all over invisible one here. So I apply the concept of reciprocal. I'll have meter all over seconds times this one comes up all over this one here comes down. Meter cancel meter. So the SI unit for velocity gradient is what? Is per second. So the SI unit is 1 over second, or s super minus 1 if you want to. So the SI unit for velocity gradient becomes per second. That's like the concept behind Newton's law of viscosity. So I've said that the shear stress in a crude element layer is directly proportional to the shear strain or shear deformation or velocity gradient. So at this point now, we are saying that the shear stress is proportional to what? Velocity gradient, the u over the y. If this is true, in mathematics, if you see a proportionality sign, you introduce what? An equal to and a constant. True or false? True. So I'll have that tau is equal to my constant here will not become k, because what? The mu. This becomes mu. So if you want to, you can call it mu or mu. So this is a Greek symbol called mu. Generally, people call it mu in science. Most generally agreed, people call it mu, but you can call it mu if you want to. Mu if you want to. So this mu here is called constant proportionality, known as dynamic viscosity. All right, before that, I'm having what? The u over the y. So I'm saying that this mu, or perhaps mu, is known as constant So I'm saying that this one here, this mu, is known as constant proportionality, known as dynamic viscosity. So this is what dynamic viscosity, mu. So I'm saying that shear stress is equal to mu velocity gradient. That is what's it called? Dynamic viscosity. So now look up, please. When it comes to viscosity, there are two types of viscosity. We have the dynamic viscosity and the kinematic viscosity. So before we dive into type of viscosity, let's get the SI unit for dynamic viscosity. So if it's for me to get the SI unit for mu, the concept is quite simple. I'm having tau is equal to mu into the u over the y. So to get if I want to get the SI unit for mu, that is make mu subject divided by the u over the y divided by the u over the y. I'll have that this one cancel this. Mu is equal to tau all over the u over the y. So let's get the SI unit of mu. We just said that shear stress is measured in what? Sorry, let me express this one here properly. I'll have that mu is equal to shear stress divided by the u over this is division sign, divided by the u over the y, the u over the y. If I spread this one here mathematically, I'll be having that shear stress here times this one comes up the y all over, this one comes down the u, right? All right, so I'm saying that shear stress, what's it called, mu, known as dynamic viscosity, is equal to what's it called, tau times dy, that's tau dy all over the u. All right, so let's get this done, please. But we know that what's it called, tau, this is shear stress, that's measured in what, in Newton per meter squared. That's for shear stress. So into velocity gradient, that's I'm having the y over the u here. So for the y is, look up, I'm having the u over the y becomes what there, what's it called, the u here, this one, the u is meter per second as we said earlier, the y is in meters. So I'm having the y up here first, that becomes meter all over the u, now becomes what there, meter per second. So meter per second, I'm having this here. For this one here, the task becomes simple. I'll have that Newton per meter squared, so into, this is meter, right, this is meter here, this one divided by meter all over second. I'm having this is meter divided by meter over second. From here, Newton per meter squared into meter times this one comes up, this one comes down. I have this one here. Of course, meter cancels out meter. I'll be having Newton times second becomes Newton second all over meter squared. So the SI unit for dynamic viscosity, known as mu, is equal to what? Newton seconds per meter squared as the SI unit for dynamic viscosity. So this is how to get the SI unit. So very important when it comes to fluid mechanics, SI units can be confusing. So I'll take my time to break them down step by step. All right, at this point here, let's discuss type of viscosity and let's see what we can do. Let's discuss types of viscosity. All right, types of viscosity. Types of viscosity. Number one there, we said there are two types of viscosity known as dynamic viscosity and kinematic viscosity. So number one there we have dynamic viscosity, and number two there we have kinematic viscosity. These are like the two types of viscosity that we have. So let's discuss these two types of viscosity one after the other. What is dynamic viscosity and what is kinematic viscosity? Let's take them one after the other. Let's discuss the first one there, called dynamic viscosity. By definition, dynamic viscosity can be defined as the ratio of the shear stress to velocity gradient. I'm saying that dynamic viscosity can be defined as the ratio of shear stress to velocity gradient. It is represented by a Greek symbol called mu. This one here, a Greek symbol called mu, or if you want to, you can call it mu. It's represented by a Greek symbol called mu, or mu if you want to. Mathematically, dynamic viscosity, known as mu or mu if you want to, is equal to, saying that the ratio of shear stress to what? Velocity gradient, the u over the y. So this is like the mathematical expression for what's it called, for dynamic viscosity, known as mu or mu if you want to. So that the shear stress is the ratio of shear stress to what? Velocity gradient. Note that the SI unit for dynamic viscosity is what? Is better than what? Is Newton seconds per meter squared, as we have derived earlier from this place here. So the SI unit for dynamic viscosity is simply what? Newton seconds per meter squared. That's the concept behind dynamic viscosity. Note that aside Newton seconds per meter squared, dynamic viscosity can be measured in terms of poise. So note that 1 Newton seconds per meter squared is equal to 10 poise. Very important. Note that aside Newton seconds per meter squared, dynamic viscosity, this one here, can be measured in terms of what? In terms of poise. So note that 1 Newton seconds per meter squared is equal to 10 poise. So to convert Newton seconds per meter squared to poise, multiply by 10. To convert poise to Newton seconds per meter squared, divided by 10. That's the idea. That's the whole concept behind dynamic viscosity, as we can chip into it. Let's discuss second type of viscosity, called kinematic viscosity. Number 2 there. Matic viscosity. Let's discuss the second type of viscosity, called kinematic viscosity. By definition, kinematic viscosity is simply the ratio of dynamic viscosity to relative to mass density. I'm saying that kinematic viscosity is simply the ratio of dynamic viscosity to mass density. Mathematically, before that, it is represented by a Greek symbol called nu. A Greek symbol called nu. Look up, please. This is not a square root. When it comes to square root, they are very simple. This one here is short, but for the concept of kinematic viscosity, the height of this one, it attains the same height as this one here. So this one is a Greek symbol called nu. It is used for representing what? Kinematic viscosity. A Greek symbol called mu, or if you want to mu, is for representing what? Dynamic viscosity. So we are saying that kinematic viscosity can be represented using a Greek symbol called mu. Called mu. So mathematically, from here now, I'm saying that nu, also known as kinematic viscosity, is equal to, we said, the ratio of dynamic viscosity to its to its mass density. Don't forget, this is a Greek symbol called rho. It's for representing mass density, as we said in last class. So try to watch our last class of introduction to fluid mechanics. So there you get the concept behind all what we are discussing here. So we're saying that kinematic viscosity is simply the ratio of what? Dynamic viscosity, this one here, to it what the mass density. So let's get the SI unit for kinematic viscosity. So what we know is that before now is that this is dynamic viscosity measured in what? Newton seconds per meter squared, right? All over, this is mass density known as rho, which is measured in what? In kilogram per meter cube. Let's combine this together and let's get the SI unit for kinematic viscosity. At this point here, express this one mathematically. I'll be having, this is Newton seconds all over meter squared. This is division sign divided by kilogram per meter cube. At this point here, I'll apply the law of reciprocal. I'll have that the SI unit for kinematic viscosity is given as Newton seconds all over meter squared multiplied by, change this one to times, take this one up, meter cube first, all over kilogram. I have kilogram. Meter squared cancel out meter cube. I'm looking at a meter here. From here now, Newton seconds times meter becomes Newton seconds meter all over kilogram. So it does not make sense to leave my SI unit like this. I'm having Newton kilogram. It does not make sense. So the idea is that I cannot say that the SI unit for kinematic viscosity is Newton seconds meter per kilogram. Is wrong. So what's the idea? I'm saying Newton. Newton represents force in what? So force represents Newton. I know that for Newton's second law of motion, force is what? Mass times acceleration. True or false? True. Mass is measured in kilogram. Acceleration in what? In meter per second. Right? Multiply these two, I'll have kilogram meter per second squared. Sorry. So acceleration is measured in what? Meter per second squared, please. Second squared. So I have kilogram meter per second squared as this one here. So it means that as my force. So it means that I'm saying that now this force is measured in Newton. I'm saying that 1 Newton represents what there? 1 kilogram meter per second squared. That's the meaning. So very important that 1 Newton, let me put this one here this way, per second squared. So I'm saying that 1 Newton now, which is force here, represents 1 kilogram meter per second squared. If this is true, anywhere I see Newton, I'll put kilogram meter per second squared. So this is Newton here. Replace this Newton with kilogram meter per second squared. So I have kilogram meter per second squared for Newton. That's for N. Multiplied by seconds, multiplied by meters. This one here. So all over what there? Kilogram. At this point here, seconds, seconds, left with 1 second here. Kilogram times meter will give kilogram meter squared, right? Kilogram times meter times meter. Meter times meter will give meter squared. Then kilogram here. So then all over seconds, like all over seconds. So this is divided by kilogram. I have kilogram here. At this point there, at that point there, so at this point there, I'll have that I have kilogram meter squared all over seconds. So change that division here to times. So there's the invisible one here. Take that one up first. 1 all over kilogram. So kilogram cancelled out kilogram. So I'm saying that the SI unit, so okay, from here, meter squared times 1 becomes meter squared. So all over seconds. All over seconds. So I'm saying that the SI unit for kinematic viscosity, known as nu, is given as what? Meter squared per second. So we have discussed several things now. Shear stress. We said shear stress is measured in what? Newton per meter squared. Velocity gradient per second. Dynamic viscosity, Newton seconds per meter squared. Yes, Newton seconds per meter squared. Kinematic viscosity, that's what? Meter squared per seconds, as you can see. So note just how they relate, how they works. Alright, with this idea now, let's solve some past questions and let's see what we can actually solve and apply. Alright, one more thing before we dive into solving past questions. When it comes to dynamic viscosity, I said aside Newton second per meter squared, dynamic viscosity can be measured in what? In terms of poise. The same thing applied to kinematic viscosity. Aside what's it called? Meter squared per second, kinematic viscosity can be measured in what? In terms of Stokes. So note that at this point here, note that 1 meter squared per second is equal to 10 to the power 4 Stokes. So it means that to convert Newton seconds per meter to Stokes, multiply by 10 to the power 4, to convert Stokes to Newton seconds per meter, meter squared per second, meter squared per second divided by 10 to the power 4. That's the concept behind this man here. Very important, please. Very, very important. Alright, let's now solve several past questions. Welcome back. Hope you are enjoying the study of fluid mechanics. If you are enjoying the study of fluid mechanics, I would like you to click the subscription button and like the video. Leave a comment and share to your friends and classmates. Right? So let's dive into solving past questions under this concept. This one says a certain oil has specific gravity of 0.95 and dynamic viscosity of 0.011 poise. What is its kinematic viscosity? Solution. So my first task in that question here, example 1, the first thing there, solution, is rather what? The givens. What am I given? I'm told that a certain oil has specific gravity. I'm given specific gravity. That Sg as 0.95, right? 0.95 as specific gravity, and dynamic viscosity. I'm given dynamic viscosity. That's what there. That's mu as 0.11 poise. Sorry, 0.011 poise. Right? 11 poise. What again there? What is its kinematic viscosity? So I'm looking for what? Kinematic viscosity, known as what? Nu. This one here is unknown. Let's get this question done. How do you find kinematic viscosity? So what we know before now is that to get this man here is quite simple. Solution. So recall that from here. Recall that we said that this man here, kinematic viscosity, which is nu, you said is equal to what? Is the ratio of dynamic viscosity all by what there? Mass density. So it means that to get kinematic viscosity, I need two things. What and what? I need to know dynamic viscosity and I need to know what mass density. Check from here. Am I given dynamic viscosity? Of course, yes. This is here 0.011 poise. Next up, am I given density? No, I don't know density. So my task sign is what? Get mass density. At this point, then, also recall that we said mass density is equal to what? Specific gravity times 1000. This was derived when we in our first class of fluid mechanics, when we discussed about the relationship between specific gravity and relative density. We derived this formula. So we're saying that mass density now, rho, is equal to specific gravity. That's 0.95 times 1000. This will give about 950 kilogram per meter squared as the S sign for what? Mass density, please. All right. So it means that I know this one and I know this one now. So let's get kinematic viscosity. So kinematic viscosity is equal to, we said, dynamic viscosity, that's mu, all over what? Mass density, rho. This one here is equal in value to what? 0.001 poise. Now, generally, I'm going to take the original SI unit for this one. So the original SI unit for dynamic viscosity is what? Is Newton seconds per meter squared. True or false? True. So it means that I'll convert this one here to Newton seconds per meter squared. So I'm given 0.011 poise. I said to convert poise back to Newton seconds per meter squared divided by what? By 10. That's the concept. If I divide this one by 10, I'll have something about is 0. So I'm saying that. All right. Let me just put it here. That mu is now equal to, after converting, I'll have 0.0011 Newton seconds per meter squared. So to convert points back to Newton seconds per meter squared, divide this one here by 10. So divided by 10, I'll have this one here. So it means that I'm using this one, not this one. So mu now, which is this, is equal to 0.0011 all over rho, mass density, that's 950. Divide the 2 here. Kinematic viscosity, nu, is equal to, if I divide them together, I'll get if I divide these 2, what do I get? Zero 0.0011 divided by 950. I have about 1.157 times 10 to power minus 6. Minus 6 what? What's the estimate for kinematic viscosity, please? Who can tell me, please? What's the estimate for kinematic viscosity? That's what there. Newton. Sorry. That's what there. Okay, that's meter squared per second. Meter squared per second as the SI unit for kinematic viscosity. That's how to solve this problem here using the idea of what we have just learned. Let's take one final example and let's end this concept. So this one example comprises of what we have discussed last class and today's class. So the example says, calculate the specific weight, specific mass, specific volume of an oil of volume 12 meters cube and weight 8 kilonewton. If the viscosity of the oil is 0.22 poise, find 0.2 poise. That's all. Solution. Let me get it done. Solution to that question. Example 2, solution. First, write out what you are given. So calculate the specific gravity. Specific weight. So I'm looking for specific weight. So is unknown. That's small w, please. Small w. Specific weight is unknown. Next up, specific mass. Specific mass. That's what that's rho is unknown. What again? Specific volume. That's small v. Specific volume also unknown. Small v is unknown. So I'm given what? Volume, that's capital V, as 2 meter cube. And also I'm given weight, W, weight, that's capital W, as 88%, 88 kilonewton. So, and I'm also given viscosity. Look up, I'm given viscosity, but which kind of viscosity is it? I'm given the value as 0.22 poise. So which one represents poise? That's what the dynamic viscosity. That's dynamic viscosity. So dynamic viscosity, which is mu, is given as 0.22 poise. All right, let's get this done. So how do you solve this one here? So what's the first task? First, understand something before we solve this one. Small w is different from big W. Small w represents specific weight. Big one represents weight. Weight. Next up, observe that small v represents specific volume. Capital V represents volume. So understand this one here. Let's proceed from here. So we're going to look for all these three parameters. So how do you find this one here? So what we know before now is that recall that we said that specific weight, that's small w, is equal to total weight all over volume. What's my weight? Of course, weight is measured in weight is what? 88 all over volume. That's 2. So I'm having 88 all over 2. Small w, known as specific weight, is equal to 44, right? 44, which is measured in what? What's the essence for specific weight? That's what? Newton per meter cube, or kilonewton per meter cube if you want to. Alright, so that's my essence for my weight there. Alright. Sorry please. The volume is 12, please. The volume value is 12. It's 12. So I have 12 here, please. 12. So divide 88 by 12. Hang on. Okay, the weight is given in terms of kilonewton. So I'll convert this one here to Newton. That becomes 88 times 10 to the power 3. This is kilo is 10 to the power 3. So I have my Newton here. So it means that the value for my weight becomes 88 times 10 to the power 3 all over 12. Divide this one here. My specific weight, small w, will be equal to 7333.33 what the Newton per meter cube as my SI unit for specific weight, as we said in the last class. That's my value for my specific weight. Alright, let's get specific mass. Let's get specific volume. So before we proceed, let's get specific mass. That's I. Let's call this one I. So for I, that's specific mass. What we know before now is that, recall the relationship. Recall the relationship between what's it called? Between what's it called? Mass density and weight density. To recall that relationship, check your note. We said that specific specific weight is equal to what? Rho times G. Recall this one very well, please. Recall that we said specific weight is equal to mass density times rho. This formula was derived when we were discussing about relationship between mass density and weight density. So we're saying that small w equals what's rho? So rho is unknown, sorry. So I'm looking for rho, that's the concept. Let's make rho subject. Rho is equal to, which is mass density, is equal to what? Weight all over gravity. Right? So now mass density, which is rho, is equal to, what's my weight? Sorry, this is not a bigger weight though. This is not a specific weight, that's small w. That's what? 7333.33. That's 7333.33 all over gravity is 9.81, as we know. 9.81. Divide these two here. So I have that my rho mass density is equal to 747.536 kilogram per meter cube as my SI for mass density, that's rho. So I'll get this one done and this one. Let's finally get my specific volume and let's end today's class. For me now, calculating for specific volume, calculate for specific volume. What we know before now is that specific volume, small v, is equal to 1 over rho. Check that we said specific volume is in the ratio of what? Total volume to its total mass, right? That's volume over mass, as we said in the last class. And I said that it's also the inverse of mass density, if you can recall very well. So we said that specific volume, small v, is the inverse of mass density. That becomes 1 over, what's rho? Rho is 747.536. Divide these two here. Specific volume, small v, is equal to 0.00134 meter cube per kilogram as my SI for specific volume. Why? We said specific volume, small v, is equal to total volume all over total mass. Volume is measured in meter cube, mass is kilogram. That becomes meter cube per kilogram. So this is how we have to solve this question here using the idea of the introduction of fluid mechanics and the concept of viscosity. So if you like this, if you understand this concept, do it to like, leave a comment and share. So see you in our next class. We'll be discussing about flow rate. So we're talking about mass flow rate and volume flow rate in our next class. So we said mass flow rate and volume flow rate. So volume flow rate is also called discharge. So looking at discharge in our last class, looking at the concept of discharge and the concept of mass density in our next class. So see you in our next class.